In this video, we'll review the theory of magnetism. Our objectives for today, we'll look at some key terms, the properties of magnets, different types of magnets, magnetic poles, permanent magnets, and electromagnets. All right, so first off, our key terms. The first thing that we have is a permanent magnet. A permanent magnet is a material that has magnetic properties and it stays magnetized. So this is like the magnets that you have on your refrigerator, horseshoe magnets, bar magnets. Those are devices that are made in factories and they stay magnetized. An electromagnet, this is a magnet that we make using electricity. And what we'll find is that when we have a wire and there's current moving through the wire, it's going to create a magnetic field. And we'll use these electromagnets in many practical industrial type of applications. Magnetized, this is what happens if we have a magnetic material and it's put in a strong magnetic field. It becomes magnetized. This is like your screwdriver in your toolbox when it sits next to a permanent magnet for too long, and all of a sudden it starts to have the ability to pick up metal shavings and things like that. Magnetic poles in a magnet, what we're going to find is that anytime we have a magnet, we're going to have a north pole and a south pole in the magnet. And this happens on the very small scales. So anytime we cut a magnet, we'll always have a north and south pole. Permeability, this is a property of materials. And this property will affect how well the material can be magnetized. And so different materials will have an ability to become magnetized. Some materials, most materials do not have the ability to become magnetized. And so we'll talk about permeability. This is something that we can measure and help us determine if we're trying to make a magnet, what would be a proper material. All right, so the first thing that we'll look at is the properties of magnets. So the property of a material to attract pieces of iron or steel is called magnetism. So when we're talking about what is magnetism, what we're talking about is, does the material, can it be attracted to iron or steel? Magnetic substances are those that are attracted to a magnet, while non-magnetic substances are not attracted to a magnet. So when we start classifying materials, there'll be materials that can be attracted to a magnet and also can become magnetized. And then there's other materials that no matter what we do, they're not attracted to a magnet. So things like iron, cobalt, those sorts of materials would be magnetic materials. They can be made into magnets and they are attracted to magnets. Things like wood and glass, paper, those sorts of things, no matter what we do, they do not respond to magnets or magnetism. There's two types of permanent magnets. So permanent magnets are magnets that stay magnetized. The first type is natural magnets. Natural magnets are magnets that are they become magnets in nature. So they're magnets that are not manufactured. You dig up the rock and it's a magnet. Typically, they have limited practical use because it's easier to make stronger magnets in a factory. So artificial magnets, these would be magnets that are made in a factory. And so it's easier to make most of the time, except when we have the case of rare earth magnets. Artificial magnets are usually better. If we have a lump of iron, it's not a very strong magnet naturally. The magnetic field will be weakened over time as it's influenced by other factors. And so if we make a magnet in a factory, take the same piece of iron and we manufacture it into a horseshoe magnet or a bar magnet, it becomes an artificial magnet. And they are made from ordinary unmagnetized magnetic materials. So we take something that's not magnetized, we put it near a strong magnetic field, and it becomes magnetized. And then a lot of times what they'll do is they'll harden the material, and then it'll stay magnetized for a long time. Both of these are what we would call permanent magnets. So in order to magnetize a magnetic material, what you need to do is you need to create a strong magnetic field. So what we're trying to do is take something that's not magnetized. So this is a bar, let's say it's an iron bar. And what they're going to do is, this is a loop of wire here. And if we push current through this loop of wire, what happens is it creates a magnetic field. If we increase the current, we could make a strong magnetic field. If we put this iron bar in this magnetic field, what's going to happen is the particles and the atoms are going to get lined up in this material. Those electrons that are spinning around in the outer orbital will get kind of aligned. And with this case, what will happen is, in our bar magnet, if we leave it there for a period of time, we'll make a north pole and a south pole in this bar. So to magnetize a material, so we're trying to turn a material into a magnet. So we're trying to make a magnet, kind of like my screwdriver in my toolbox. It's sitting next to a magnet and it becomes magnetized. We take a magnetic material and a DC, it's got to be DC, we'll talk about why in just a second, voltage source is momentarily applied to the coil leads. So basically we take a magnetic material, we put it in an electromagnet, and it becomes magnetized. If we want to demagnetize the same bar, what we would do is we would connect an AC circuit to here. If we do an AC circuit, what happens is if we had an AC source, okay, so we apply an AC source to our loop of wire, what will happen is during the positive cycle, this becomes a north and this becomes a south, just like the DC. But then in an AC source, it's positive for a little while and then it goes negative. When it goes negative, what happens is the current goes the opposite way, which means that we would get, so let's say during this cycle, it's negative. That means that the current would go in the opposite direction, which means we would get a south pole on this side and a north pole on this side. So when the current is going in the positive direction, we'd get current in this direction during this cycle. And so what's happening is, in this bar, it's going to go from north pole, south pole, north pole, south pole, and that's going to scramble those magnetic particles inside the magnet. They're not going to become aligned, and it doesn't become a strong magnet. So if we have something that is called a permanent magnet, it has to retain its magnetic properties for a long period of time. So we magnetize the material, it becomes a magnet, and when we take the item away from the magnetic field, it has to stay magnetized. Okay, so like if I have my screwdriver, I take it out of my tackle box or out of my toolbox, and I go and touch a piece of a nail or something like that, and it attracts the nail. It stayed magnetized, that's what we would call a permanent magnet. Temporary magnets are magnets that they only act as magnets as long as it's in the magnetic field produced by a permanent magnet or an electric current. So a temporary magnet would be a material that while it's in the magnetic field, it's magnetized, but as soon as we take the magnetic field away, it's demagnetized. Later on, we'll talk about things, solenoids and relays. These are devices that have magnetic materials, but when we take the current away, they become demagnetized. They do not retain their magnetism. These would be what we would call a temporary magnet. Magnets can be made into ceramics and molds like this for applications like motors and other things. And when they're making a ceramic material into a magnet, they're often referred to as ferrites, and they're made by combining iron oxide with particles from the ceramic compound. So ceramics on their own are not magnetic material, but if we put in iron oxide, so little iron particles in the ceramics, it can become a magnet. They can be molded into different shapes. They're non-conductive, so they do not. That means that they have a high resistance, and so they do not conduct electricity. No current. That's probably what I should have put. They have a very high electrical resistance, so they don't get current to flow through them. So they're still an insulator, but they are a magnet. All right, so let's look at the laws of magnetic poles. So if we have a magnet, let's say we have a magnet here, what we would find is that there's going to be, at the end of the magnet, there's going to be a north pole, and at the other end of the magnet, there's going to be a south pole. If we cut the magnet in half, what we would find is that we would end up with two magnets, both having a north pole and a south pole. So even if we were able to cut these magnets all the way down to the atomic level, we would still get a north pole and a south pole. The north pole and the south pole come from the electron spinning around the outer orbital of the atom. So all the way down to the atomic level, we'd have a north pole and south pole. So we can't have one without the other. The law of magnetic poles states that like poles repel and unlike poles attract. So if we have a north pole on one magnet, that'd be attracted to a south pole on the other magnet. If we have a south pole and a south pole, they're going to try to push each other away. Later on, when we look at applications, we'll use these poles or these laws of magnetic poles to create magnetic machines where we're trying to push and pull different materials away from each other. We'll look at things like electric motors, linear motors, and things like that that use these poles. A horseshoe magnet is a bar magnet that you push or bend into a horseshoe. And so you have, anytime we have a magnet, the strongest part are at the poles. So when we look at these field lines, these are field lines. When we get more field lines in one area, so if we made just like a circle here, and then we make a circle here, the more field lines you get in that circle, if the circle's the same size, would mean that it's stronger. So all magnets are strongest at the poles. So if we have a horseshoe magnet, what we're doing is we're putting the two strongest parts of the magnet closest to each other. So a horseshoe magnet is a bar magnet that's been around in the shape of a horseshoe, and you get a much stronger magnetic force when you connect the magnet this way. Other types of magnets, so our Earth is a natural magnet, and that comes because we have an iron core, and the electrons in the iron core are moving as the Earth spins, and it creates a very large magnetic field, which is a good thing. It shields us from the sun, and also it allows things like compasses to work, so we can tell which direction is the North Pole. And the magnetic pole of the Earth is near the geographic North Pole. It's not exactly, so the geographic North Pole would be in the exact top of the Earth would be the North Pole. The magnetic North Pole it kind of varies depending on the time of year, but it's near the geographic North Pole. If we have a compass is a device that allows us to determine the polarity of a magnet. So in the compass, the south pole of the compass is attracted to the north pole on the magnet. So if we flip the magnet around, if we look at this string, so this is a example of a magnet with a pointer on a string so it can spin. So that's what this is. And so what we'll find is that the south pole on the magnet, so this is blue, so this is the south pole on the compass's magnet, and the red here is the north pole on the compass's magnet. And this is allowed to spin. So if we put a magnet, a permanent magnet near it, so here we have the north pole of this magnet. What's going to happen is this is going to turn, and the south pole is going to be attracted to the north pole on the magnet. And then if you're trying to find so the compass will align itself with whatever magnetic field is near it. And then if you're trying to determine what direction that is, you kind of spin this around, and then you could tell which is north and which is south. When we're looking at a magnet, there's an area around the magnet that's called its magnetic field. The field will show the strength of a magnet, similar to, like, let's say that we were looking at a lake. So this is my graphic of a lake. And if you've ever seen like a topograph of a lake, you might see stuff like this where it has like equal lines. So like maybe this part of the lake is all 5 feet, and then this one is like 7, and it starts getting deeper. And what you'll find is that if you look at that graphic of the lake and you have more lines, that's showing a drop off. So if you're going to go fishing and you see this map, a lot of times fish like to be on the drop offs, and so that's where you would try to fish, where you'd see a lot of lines. In a magnetic field drawing, the places that have a lot of lines here aren't the drop off, that's the stronger parts of the magnet. So the magnet is super strong, it'd be the strongest we're at the location that has the most of these lines. So right here and right here would be the strongest part of the magnet. You can create these by taking a piece of paper and putting it over a magnet and then dropping like iron filings onto the paper, and you'll see how the iron filings will kind of line up to show these kind of field lines. And this is a invisible line of force. Sometimes what we'll call that is flux. So we'll call this the magnetic flux lines. These individual lines, this is the magnetic flux lines. And if we were comparing two different magnets and we could see the chart of the magnetic flux lines, we could see that magnets that have more lines would be stronger magnets. It'll also help us to determine the direction of the magnetic fields. When we have magnetic fields near current carrying conductors, it can cause problems. Magnetic fields, varying magnetic fields, induce currents in wires, and that could be a problem. And so there's a whole line of study which is called magnetic shielding. And the purpose of magnetic shielding is to prevent magnetic fields from interfering with the electrical devices or signals. So you might see this maybe if you had like a amplifier in your car for a speaker system. You might have some pretty elaborate magnetic shielding devices in the circuits. These wires have, a lot of times they'll have wire braiding and then aluminum foil on the inside the wire in order to limit the effects of the magnetic fields. So magnetic fields, especially varying magnetic fields, will cause current to flow in wires. We're going to use that later on to generate electricity, but it can cause problems, especially for electronics. So when we put shielding inside a cable, this is called a shielded cable. You may have heard of that at work. A lot of times we'll use shielded cables for things like prox sensors or variable frequency drives or transducers, sensors, those sorts of devices will use shielded cables. And the goal is to limit the coupling of a magnetic field by providing an alternative good conducting magnetic path. And so what they do is you put this metal foil in here and then you ground on one end only the shield. And so if there's any currents that are induced inside that foil, it immediately gets transferred to the ground. And so you don't get current flowing in your conductors. There's two kind of theories of magnetism that we'll go over. The first theory is that when you have a bunch of atoms inside a material, they form these kind of small magnets. So we're talking about many, many, many atoms inside a substance. And not all substances can create atoms. If you watch the previous videos, kind of what we found was that they have to have a certain electron structure in their outer orbitals in order for them to create these small magnets. If the electrons in the outer orbitals are balanced, they won't create a magnet. And so only certain materials have the, kind of the perfect electron structure in order to create these small magnets. And so what happens is when their material is unmagnetized, these small magnets are all kind of random and they don't add up together. And so like, it's like if we looked at these ones, they're kind of canceling each other out. And so you don't get a very strong magnetic field on either side. The same thing happens if you had like in one of the videos, the guy talks about how, if you have this rock and maybe this part of the rock is a pretty good magnet, but the other parts of the rock are not good magnets. And so the whole rock winds up being not very magnetic. Okay. If you put this same bar into a strong magnetic field, what will happen is these particles will move and they'll all become lined up, and then it becomes a magnetized bar. So it's like the magnetic field is reorienting these small magnets, so they're all working together and cooperating, and we end up with a strong magnet. When we talk about this in terms of electrons, what's happening is the magnetic field is shaping the direction of the way the electrons are spinning around their outer orbitals, and they're creating, it's kind of aligning all of the magnets, or all the electrons. So the electron theory of magnetism, which looks at one atom and the electrons that are spinning around that atom. And the idea is if we can take these atoms and get the electrons to all spin in the same direction so that they create their magnetic fields don't cancel each other out, we can make that material magnetic. And so some materials have the ability, depending on how many electrons they have in their outer orbital, some of them have too many and then they'll cancel out. And so if you have just the right number of electrons in your outer orbital, and those can be influenced by a magnetic field, and they can become all lined up, then that material becomes magnetic. And so if you put it in a magnetic field that has a, if this is a north pole and this is a south pole, this would be south and north on our big magnetic field. So it's trying to line up those electrons, then it becomes magnetized. If we take an electromagnet and we put AC current through it, and it starts to scramble those, so we get a north pole, south pole, north pole, south pole, then we can go back to being unmagnetized. So the materials can be magnetized and demagnetized depending on the magnetic field that they're that's close to them. The next thing here, we have a definition. One of the terms that we're going to care about for this section is permeability. It's also used in mu, which is the micro for us, so it's a little confusing. We're not going to worry about the letter, just the definition. So the permeability is a measure of the ease with which magnetic lines of force pass through a material. Materials that are easy to magnetize have a higher magnetic permeability. And so this will be what determines whether the material can become a magnet, if it has a high permeability. Next thing is there's a magnetic field anytime that we have a current carrying conductor. So we've talked about electromagnets, and if electrons are moving, which is why when we had our magnetic materials, electrons moving creates a magnetic field. That's what creates the magnetic field. We can figure out what the lines of force are and the magnetic field around a current carrying conductor. And there's some different rules that we'll use. This textbook uses electron flow, so we're always going to use the left-hand rule. If you've watched some other videos on YouTube, they may talk about the right-hand rule. Use the right-hand rule if you're using conventional current flow, which we're not. We're using electron flow for this class. And so what we'll be able to do is we'll be able to determine, depending on the direction of current flow, what the magnetic field looks like. So this is showing, it's trying to show these are conductors. So this is like an end view of the conductor. So this little circle here is supposed to be like a cylinder. And here we have current, and the X means that the current is flowing into the board. So we're going to say that the current in this cylinder is flowing this way. And what happens is when I have two conductors and the current is in the same direction, there's actually going to be a magnetic force that's going to push these two apart. And I don't know, I'm not sure why this is showing these arrows this way. I'm going to cross these out. So this means that they're going to try to repel and move each other apart. Now this is not a very strong force. So if we had two wires and they had like maybe 10 amps flowing through them, it would be very difficult to measure that force. But these current carrying conductors do create a magnetic field, and they'll try to push each other apart if the current is going in the same direction. If the currents are going in the opposite direction, so this is a wire here, trying to draw it in 3 dimensions a little bit here. This one would have current coming out of the board, and this has current going into the board. These two are going to be attracted, and they're going to try to draw each other closer together. So anytime we have electric charge moving, it's going to create a magnetic field. And depending on the direction of the current flow, it's going to create a north and south pole that's either going to attract, or repel the conductors near it. If we take that idea and we take our wire, and rather than keep it in a straight line, we make a loop of wire, what happens is we can create a north pole and a south pole. So a loop of wire is going to create north and south poles. And so if we have a coil of wire with several parallel conductors carrying current in the same direction, what will happen is the magnetic field that they create along their axis here will create the north and south pole, and that'll be very similar to a magnetic field that's created by a bar magnet. All right, so this is when we have a conductor. So let's say, so we'll try to draw this. So here I have a bar, and it's made out of a temporary magnet. So it's not going to stay magnetized. So it's only going to be a magnet as long as there's a magnetic field. So usually what we would do to make a temporary magnet like this is we would use a soft iron core for this. So it's not going to stay magnetized. Okay. So now what I'm going to do next is I'm going to take a DC supply and I'm going to wrap around the DC supply my coil of wire, or a coil of wire. So if I showed this with a side view, which is a little bit easier to show, my side view of this would look like that. And here is my, so we're showing that the wire goes behind first and then in front. Okay, so here's my circuit. And the left-hand rule is what's going to tell us what is a north pole and what is a south pole. So when we use the left-hand rule, what we do is we look at the current's flow direction. So current is flowing in this direction. And then what you do is you take your hand and you take your, what you're going to try to do, and I'm going to try to show this, and I'm not very good at drawing. So here's my fingers. And here's a thumb. And so what I'm trying to show is that your fingers would wrap around, man, I'm bad at drawing. Okay, and so then what we do is we take the our fingers and we wrap it around the bar. So in this case, here is our bar. And there's some better graphics of this in the book. And our thumb, which is here, you kind of point out, and your thumb is in the direction of the north pole. So this would be north, and this would be south. And so for this one here that I drew, we go over the bar first. So you use your left hand, this has to be your left hand. And that goes over the bar, and then your thumb is in the direction of north. So if we look at this coil here, which they have a much better graphic, they're showing current flowing through this way, and it's going around. Okay, so he's taken his fingers from his left hand, and they're in the direction of the current flow, which they're showing with these arrows. And then his thumb is pointing, him or her thumb is pointing towards the North Pole. Okay, so that's the left hand coil rule. So let's say that we have another one. So let's do a different one. So I'll draw this down here. So here is our supply, and we have some wires, and this time we go around this way first. Okay, and let's say that current is flowing in this direction. Okay, so I'm going to try to make another one of these fantastic drawings here. It's a lot easier to demonstrate in a live class. So here's my bar. Okay, and again, we're going to use our left hand. So it's like here is our oh my gosh, I don't even think I can draw that. It's like the inversion of this one. And so if we wrapped our hand around this way, what we would find is that our thumb, I'm making myself laugh here with this fantastic drawing, is in this direction. So that means that this is the North Pole and this is the South Pole. Not an artist. Okay, so hopefully that explains it a little bit. I would consult the book for some better pictures of this. So when we look at this picture, we should get North Pole over here and South Pole over there. So here's some other examples that are a little bit better. So here we're looking at the magnetic polarity of the coil, and depends on which direction the current flows and how the current is wound. So there's actually 4 different versions of this. And so if we look here, this one goes back first. So we have our hand behind the wire. And so I'm intrigued by trying to draw these now. So I take my left hand. So here's my fingers. And then here's my thumb. Oh, that's a great picture. All right, and then here is our conductor. And so our fingers are in the same direction as the current flow, which means that this would be our North Pole over here and our South Pole over here. And make sure you always use your left hand. For this one, the current goes over first. So we would have, if this was our fingers and our thumb, the bar would be behind our finger and our thumb. And so as we put our finger over, our thumb is pointing towards the North Pole. And so this would be the North Pole and this would be the South Pole. And so if we're showing the kind of like the bar on top, that would be like this. And then if our fingers were on top, I guess we could show it like this. Okay, so that's our fingers on top of the bar, and then the thumb is still pointing towards the North Pole. Earlier we talked about that if we take an electromagnet and we have a soft iron core, it can be magnetized temporarily by passing current through the coil of the wire. So this would be an example of a temporary magnet. And it's only a magnet when we attach current flowing through the wire. When the current doesn't flow through the wire, there's no magnet. And so you can use this here as a kind of a pick up and drop system. So we energize the magnet, and we pick up stuff, we move it to another location, and then we drop it. That's kind of the basics of magnetic pickups, like for pick and place robots and things like that that are picking up metal, sheets of metal or metal parts. Factors that affect magnetic field strength of an electromagnet. The most important thing is the core material. So if you have a good core material or a bad core material, that'll be the most important part of your magnet. The number of turns on the coil and the spacing of the turns, and then the amount of current. Basically, the idea is we're trying to get as much amps in the smallest space. So we're trying to get as much amps as in the smallest space. So if I take these, this is the number of turns here, or the spacing. If I could shrink this down and take all of these coils and bring them this way so that the spacing of those coils was smaller. So I kind of grab these coils and push them all down here. Then I would have more current in a smaller space. So that would be a better magnet. So if I increase the turns, that's going to be a better magnet. If I decrease the spacing, but keep everything else the same, that's going to be a better magnet. If I increase the current, that's going to be a better magnet. If I make the core material's diameter, so we start off with this, if I go to a bigger diameter, that's going to be better. So this would be increasing the area, the cross-sectional area. That's going to be better. And what we'll find is that a lot of times the way that they make these magnets is they make like a donut. It winds up being like like a pancake. A pancake design is what we'll see in a lot of the electromagnet. When they make electromagnets, a lot of times we'll see that kind of, especially if we want a real powerful magnet, they'll make it and it'll look like a pancake. There's some other properties. Electromagnetic induction. This is going to be very important for things like motors and generators, which are some of the most common electrical machines that we're going to deal with in more advanced classes. Electromagnetic induction excuse me, of a voltage by a relative motion of a conductor across a magnetic field. So what this means is if I move a permanent magnet near a coil of wire, and it has to be moving is the most important part, is while that magnetic field is changing, the coil of conductor will try to make a north and south pole. And so if you take this magnet and put it into the coil and then back out, what will happen, so we're taking it and going, all the way in and then back out. What will happen is this coil of wire will try to turn into a north pole and then a south pole as the magnet moves back and forth. And so if we take this permanent magnet and move it into the coil and out of the coil, we'll actually generate a voltage. And that's going to be very important in our motors and generators. So magnetic induction is also used, I should put motors and generators and transformers. And so if we have a varying magnetic field in a coil and we have another coil near it, we'll actually induce a voltage in the other coil. Just like when we have a wire next to another wire, if we have a varying current, it'll induce a current in the other one. Take a coil of wire, it'll do the same thing, but much more efficiently. And so this is kind of the basis for making a transformer. And we have a whole section on that in this class coming up later. But the idea is if I take a varying magnetic field and put it next to an electromagnet, it'll generate, or it'll produce a varying voltage on the other coil. And the idea is that if this one's a north pole and this one's a south pole, it's going to try to make this one into a north pole and this one into a south pole. But as they keep changing due to the sine wave, it'll make this one a north pole and this one will try to be a north pole and then this one will change, and then they'll keep changing, and we'll actually get a AC voltage out of the second coil. All right, that's the end of this video. Thank you.